Welcome to rational functions that are reducible. So today we're going to be graphing rational functions that can be reduced. They have a common factor, number 6. And in the next lesson we'll graph number 5, where the numerator has the greater degree. So rational functions can have two types of discontinuities. We've seen one of them, and that's our vertical asymptotes, and now we're going to learn another one. So we have what's called a removable discontinuity. Is present when the function has a common factor in the numerator and the denominator. A vertical asymptote is present only when the denominator is equal to 0, and that's after reducing, if possible. Okay. So we're always going to be looking for our removable discontinuities before we find the asymptotes, right? We have to do that first, right? And really it's as simple as factoring and seeing if you have any like factors in your numerator and your denominator. Right? So we always have to find the removable discontinuities first, and that is in your notes, right? Removable discontinuities don't create vertical asymptotes. Removable discontinuities create holes in our function. Okay, so not vertical asymptotes. So we want to make sure we find those first so we graph our function correctly. Okay. So let's take a look at some of these. I added this to the lesson, and I did that after I printed out your notes. I'm going to give this to you as part of your notes on Tuesday. So just follow along. And anything I write on here, by the way, on this page and the next 2 pages is going to be part of your notes anyway, so you don't have to write it down. Just follow along. So vertical asymptotes or holes occur where a rational function is undefined. Undefined means that the denominator equals 0. And we haven't had any rational functions with holes, but now we will. So a hole will occur on the graph of a rational function when the function has a common reducible factor in both the numerator and denominator. So to find the x-coordinate of a hole, we're going to set each reducible factor equal to 0 and solve for x. Anything you could cancel out, that's a reducible factor, and you're going to set it equal to 0. But you need to know the y-coordinate. That just gives you the x-coordinate. To find the y-coordinate, you're going to plug the x value of any hole into the most reduced form of the function. It does have to be the reduced form. If you don't use the reduced form, you just end up with 0 over 0. Because functions are undefined at holes, the x values where holes occur cannot be in the domain. So we have to take out, so we're going to take vertical asymptotes and x values of holes out of the domain. So a vertical asymptote is an imaginary vertical line that will occur on a graph of a rational function where the function has factors only in the denominator that do not reduce. Right? So it's what makes our denominator equal to 0, and it's factors that we couldn't cancel out. So if x approaches k, y approaches infinity or negative infinity. It just gets larger and larger or smaller and smaller when we have our vertical asymptotes. To find the equation of a vertical asymptote, you're just going to set each reducible factor in the denominator equal to 0 and solve for x. A graph of a function cannot cross a vertical asymptote. And because vertical asymptotes are undefined, because functions are undefined at vertical asymptotes, the x values where vertical asymptotes occur cannot be in the domain. Right? So we're going to take vertical asymptotes and holes out of our domain. All right, so here we have an example of a rational function with a vertical asymptote and a hole. So the equation of the vertical asymptote is that x equals -2. Right? That's our vertical asymptote. Notice, so this is the vertical asymptote. Notice the hole right there in our graph. And see, we represent that hole with an open circle. That's telling that there's a hole there. Right? So where does that hole occur? Well, I'm going to have to estimate a little bit because it's at a fractional value. It's definitely at 2 on the x value. It looks like maybe a fourth. Looks like it might be a fourth. So we have a hole at 2 1/4. That value just does not exist in our function because, well, 2 was a fact. X minus 2 was a factor that we canceled out. Right? And because it was once a 0 in the denominator, we can't include it. Let's take a look at some equations of functions, and I think that'll make it even easier. So this is what it looks like visually. Let's see what it looks like algebraically, and let's find some vertical asymptotes and holes. And I will give this to you as part of the notes. This is some of the stuff I added. All right, so vertical asymptote. So we have f of x equals x minus 2 over x minus 3. All right, so nothing to reduce there, right? X minus 2 and x minus 3 don't match, so we have no holes. But we do have a vertical asymptote. If we set x minus 3 equal to 0, we have a vertical asymptote at 3. Let's look at the next example. Now this one could be factored. Multiplies to give me 6, adds to give me -5. That's -3 and -2. So we have x squared. Actually, I'll write that up here. Multiplies to give me 6, adds to give us -5. That's -3 and -2. So we have x squared minus 3x plus -2x plus 6. And the first two are a group. Oops. I did not mean to include my plus sign. And the second two are a group. And we'll pull out the x, and we have an x minus 3. We'll pull out the -2. We have x minus 3. So that could be rewritten as x minus 2, x minus 3. All right, so that means our function here is x minus 2 times x minus 3. And we have x minus 3 in the denominator. Well, we could cancel that out. So now if we cancel out x minus 3, our function is now just x minus 2. That's all that's left. But I can't include 3. Even though we don't see it in the reduced form, it was there in the original. So if it's there in the original, we can't include it. All right, so we have no vertical asymptotes because there's no denominator left. There's nothing else set equal to 0. But we do have a hole, right? So here, if I can't use 3. We canceled out 3. So we have a hole at 3, right? Because if x minus 3 is 0, I can't use 3, right? Because it was in the denominator. Now, if I plug 3 back into this reduced form, if I plug it into the other one, I'm going to get 0 over 0. But if I plug it into this one, I get 3 minus 2 or 1. That means there's a hole at 3, 1. There we have a hole. All right, let's take a look at the next one. Okay, so we can factor this one. And actually, I'm going to stop this tape at 10 minutes. It keeps the size a little smaller, and then I'll pick up again after 10 minutes. So we have f of x equals x squared plus x divided by x squared minus 2x minus 3. In the numerator, we can just factor out that x there. I'm going to write in a different color. Maybe I'll write in red. And so we have x times, if I divide both of those by x, I'm going to have an x plus 1. In the denominator, multiplies, just do it down here, I guess, multiplies to give us -3, adds to give us -2 is -3 and 1. All right, so that would be x squared minus 3x. And x minus 3, we can factor out an x, and we have an x minus 3. Factor out, a 1. because they don't have anything in common. And we have x minus 3, so factored, this would be x plus 1 times x minus 3. All right, so our equation is really x times x plus 1 over x plus 1 times x minus 3. All right, well, look, there's an x plus 1. And I suppose I should put f of x equals. F of x equals, there we go. We could cancel out the x plus 1s. So in reduced form, wish I gave myself a little bit more space here. I put too many problems on one page. In reduced form, we would have f of x equals x divided by x minus 3. So we do have a vertical asymptote, right? So when x minus 3 is 0, x equals 3 is a vertical asymptote. We canceled out a factor, so when x plus 1 is 0, or x is negative 1, we have a hole. Now we just need the y value. So f of negative 1, we have to plug it into the reduced one, would be negative 1 divided by negative 1 minus 3. So that's going to be a positive 1/4. So we have a hole. Our function has a hole at 1/4. There's a hole there. I'm going to stop this tape, and then I'm going to pick up with the last two problems. See you in a moment.